All right, the Poisson distribution. The Poisson distribution is basically used to model the number of times that an event will occur, all right, in a fixed interval of time and space, given that these events occur with a known average rate. All right, so there's a known average rate. So a known average rate means that you know how often it's occurring on average. And this can be a hypothetical, and we'll go through an example as well. The next thing is that it's independent. All right, so it's independently of time, independent of the time since the last event, of the last event. So we normally use this in example of fields where we would use the Poisson distribution would be, for example, in insurance. We would use it in finance. We would use it in telecommunications, and we can model events such as like accidents or defects of something in the manufacturing industry, or calls, the number of calls that take place. And what we need a single parameter here. All right, the parameter that we use is known as lambda, and it's pronounced lambda, right? And lambda basically is the average rate of occurrence of an event. All right, so that's the definition of the Poisson distribution, basically. And what we need to do now is look at the next thing. All right, so let's look at an example of this. All right, let's look at an example of the Poisson distribution. All right, jump into an example. All right, so let's say we have to search results, and we know that Tokyo is the most populous metropolitan area in the world with an estimated population of 37.468 million residents as of 2018. Although this number is gradually decreasing since then, the prefecture itself has a population of 14.09 million. As for the current population in 2023, we couldn't find a reliable source that provides an exact number, but basically the population density of area of Tokyo as an area is about 6,224.66 people living per square kilometer, which indicates that Tokyo is densely populated. All right, so this is where we're talking about population. Okay, so let's have a look at an example now in terms of the Poisson distribution and how it applies in that way. All right. So here's another one. Let's say that we got a call center that receives an average of about 10 calls per hour. Okay, so we got a call center that receives 10 calls. Okay, so this is a slightly different question. 10 calls per hour. We can use the Poisson distribution to model the number of calls the call center receives in a given hour. The probability of receiving exactly k calls in an hour, where k is non-negative integer, is given by the Poisson probability mass function. Right, it'll be given by the probability of k occurring is equal to lambda to the power of k, right, multiplied by e to the power of negative lambda all over k factorial. Okay, and this is the Poisson distribution formula that we would use. Okay, lambda is the average. So, for example, let's say the probability of receiving exactly 8 calls in an hour, the probability of receiving exactly 8 calls in an hour will be given by the probability of k equals to 8, which will become 10 to the power of 8 times e to the power of negative 10 divided by 8 factorial. All right. Now, similarly, if we had to calculate that, now if we put that on a calculator, we have to find our E button, make sure we know where that is. We put it on a calculator and let's see what it comes to. It'll come to a decimal and it'll come to 0.1126. That's, yeah, so 0.1126. All right. So using a calculator, it's the best way, right? Once you have a calculator. Similarly, the probability of receiving at least, now the word's going to change it, right? The probability of receiving at least 8 calls in an hour means that we want to find a probability that the random value x is greater than or equal to 8, let's say. All right. So that's going to be equal to the probability 1 minus the probability that x is less than 8. Because if it's greater than or equal to 8, starting at 0, it's the same as from 0, 1, 2, 3, 4, 5, 6, 7, 8 individually. So we say 1 minus that probability, which is going to be 1 minus the probability of 0 plus the probability of 1 plus the probability of 2 plus, and we just keep continuing, plus the probability of 7. Then we're done. Okay? And this comes to 0.2593. Okay, so this example basically shows you how the Poisson distribution can be modeled, the frequency of events that can occur. All right, let's have a look at another example. It's example number 2. All right, suppose a call center receives, so again, we've got a call center and it receives 20 calls per hour. So after 1 hour, it will ring 20 times. We can use the Poisson distribution to model the probability of receiving a certain number of calls in a given hour. Let's say we want to find a probability of receiving exactly 25. So example, the probability of receiving exactly 25 calls in an hour. Given that the probability x is equal to some k value is equal to e to the power of negative lambda to the power of k over k factorial. And remember that e is basically equal to 2.71828. Lambda is your average rate of events, and k is equal to the number of events. All right. So the probability x is equal to 25 is going to be given by e to the power of negative 20, because that's lambda, times 20 to the power of 25 over 25 factorial. Using a calculator, we can compute the probability to be approximately 0.044. All right. So the probability of receiving exactly 25 calls in an hour when the average rate is 20, given that on a normal day, in 1 hour, so that means I've got a clock here, in 1 hour, we're going to have 20 calls. We want to find the probability of getting 25, right? Which is more calls. It's plus 5 more. So they're saying you will get 5 more calls 4.4% of the time using this as a probability, which means the chances of us increasing all the way till 25 calls would be 4.4%. What if it goes to 21 calls? If it goes to 21 calls, then we put 21 in there. Then we would have the probability of X equals to 21. And let's see what this number comes to. Because 21 calls is closer to 20. So we'd expect a higher probability because it's close to the average. So let's have a look. So negative 21, 21, 20 to the power. This is going to be 20. So let's go back there again. 20 in the power, and it's going to be 20 to the power of 21 over 21 factorial. Okay, so that's the thing there. What we do now is we calculate that on a calculator, and it comes to e to the power of 20, 20 to the power of 21, 20 factorial comes to, all right, let's just double check that. So that's e to the negative 20 over 21 factorial. So that's going to be coming to, this comes to 0.0846. So there's an 8.46% chance that it will become 21 calls. 21. I mean, yeah, 21 calls in 1 hour. The probability of it being 19, let's go, the probability X is equal to, or even lower than that, let's say 12. So I keep this on my calculator. All I have to do is just change 21 into 12 and then change 21 factorial into, so that's going to be to the power of 12. And I just change my denominator into 12 factorial as well. And that actually comes to 0.0176, which is a 1.76% chance of it being so low. So it won't even get that low. Well, it will, but with a low chance. It has a higher chance of getting to 25 than it is to getting to 12. And so we can form this distribution, which is your Poisson distribution, of predicting something happening. All right. Okay.